My name is Nick Davis, and I'm the Product Development Engineer at CP Group. We're here to talk about the future of mechanical screening. Bold claim, right? Yet, at the same time, I'm sure a few of you are wondering why we are even bothering to talk about boring old mechanical screening in a world full of robots and artificial intelligence. Well, the reality of robotics is slightly different from what we see in fiction, either in movies or maybe in advertisements. Industrial robotics rely on repetition and consistency, and if anyone has ever been in a MRF, you'll know our material is very inconsistent. It is, perhaps, the most heterogeneous material known to man. Mechanical screening serves to even out and reduce the flow, increase downstream homogeneity, and decrease burden depth so that any sorter, manual, optical, or robotic, can function more efficiently and at higher throughput by giving sorters the repeatability, consistency they need. So, in this webinar, you will learn the difference between screening and sorting, how screening aids and enables the various types of sorting, the historical types of screening and the challenges, how changes to the solid waste industry are driving innovation in mechanical screening, and what mechanical screening will need to become to enable the MRF of the future. From a 10,000-foot perspective, we should consider that the end goal of a MRF is to create sorted products. And so take a look at that definition. Sorting is a yes-no decision about every item or just about every item that enters a MRF. That's a lot of decisions. Just imagine taking an entire tip floor full of material, spreading it out so each item can be seen individually, and then making a decision on that item and the next and the next and so on. So, that's why we have conveyor belts and such. Thanks, Henry Ford. But still, in order to make a decision with precision on every item, we need to spread it all out so we can see every item, which means limited throughput per sorting station. And you also don't want people or machines looking at and making decisions on items that they aren't targeting. Someone who is sorting PET bottles, making a no decision all day on pieces of paper isn't doing any good. So again, at a high level, there's a decision minimization strategy. Each decision costs money, so we want to minimize no decisions to minimize total decisions. And that is where screening comes in. Because the great thing about screening is that it is dumb. Let me assure you, no decisions were made in the fractionation of these material streams. Screening is a rough cut based on mechanical properties, and because each item doesn't have to be inspected, the constraints we discussed about with sortation go away. Screening is then high throughput and robust, and is used to send the right material to the right sort station by fractionating and concentrating the stream. If we consider an old school serial approach to sorting, we can just put everything on a conveyor belt and sort one item at a time with a bunch of people or robots or whatever. A flow diagram for that would look something like this. If we want more throughput, we can just add lines and we get here. 4 sort lines, 32 sort stations, done. But remember, sorting is expensive. So if we add screening to fractionate and concentrate the material, we end up with a diagram more like this. With 2 stages of screens, we still end up with the same 4 sort lines, each with 2 unique sort stations, for a total of 8 sorted commodities. This is, of course, a simplification. Screening isn't perfect, so in a real-world flow diagram, you end up with lines all over the place, but you get the idea. Now this, in theory, saves money, because not only should screening be cheaper than sorting due to the lack of decision-making, there are also fewer machines due to the higher throughput of screens. I'm sure there are ops managers and maintenance people out there going, yeah, about that statement, after having cleaned screens about 1 million times. But stick with me, this is where the future part comes in. But before we get to the future, we're going to talk about the present and how sorting works today, and we're going to talk about the past and how screening has been done historically and the strengths and weaknesses of various machines. We're doing this so that we can establish a mental framework to think about what the screens of the future should do, and then we'll go back to the future. There are currently 3 means of sorting: manual, optical, and robotics, and roughly 3 locations for sorting: the pre-sort, the fiber sort, and the container sort. First, I want to talk a bit about positive versus negative sorting and how this has been used in the past along with screens to minimize the work a MRF has to do. Positive sorting is the type of sorting I've referenced so far. See item, 1 item, pick item. Straightforward. Negative sorting, also called quality control sorting, is where you pick all the items you don't want in a sorted commodity. For example, if you're negative sorting OCC, you pick off the buckets and the scrap metal and the film plastic and let the OCC pass by. It used to be, back when the material was all OCC and newspaper and milk jugs, that the items coming out of the mechanical screens were 95% of the way to being sorted already. So you could put maybe 1 QC person on the OCC and 2 to 4 people on each paper QC line, and for the most part, things worked and effort was minimized because we were only actually sorting 5% of the material. And then on the container line, you could do whatever sorting made financial sense. It was, more straightforward. But then newspaper went away and Amazon happened and packaging diversified and contamination went up. And here comes flex packaging. And the paper QC line went from being 5% contaminated to 25% contaminated. It takes 5 times more effort to get 25% out rather than 5% out. This is where optical sorters for paper start to really make sense. And yes, 5 times 4 is 20. I've seen paper sort lines of 20 people. I'm sure others have as well. 20 people is about 1,200 picks per minute, which is less than what some optical sorters cleaning paper do. So, with the declining efficiency of screens due to changing material streams requiring more sorting, what use are screens? Glad you asked. Let's get to how screens help various sorters. Manual sorters. We should all be familiar with manual sorters. They're people equipped with this fabulous piece of AI called a brain. They are the most flexible sorters available to us. They can work at any position. They can change on the fly. They can actually move to a new sort station if needed. They're also capable of knocking down surges in case we haven't thinned out the stream enough. But they have a limited pick rate. They only have 2 arms. They also come with all the drawbacks of labor working in a somewhat dangerous environment. Like all sorters, they benefit from screening, but they are the only sorters who can work at high throughput without screens. Robotic sorters are the current sizzle in the industry, but they have a lot of limitations. They have a low pick rate, typically lower than manual sorters in practice, but also an inflexible pick rate. If a robotic arm is capable of 60 picks per minute, what it really needs is about 1 pick per second. If 5 items come across at the same time, 4 of them will be missed. If there's a 10-second period with no items, the effective pick rate will drop. This is the problem with having only 1 effector, which has to move to the target item rather than having the target item come to it. It is also important to differentiate the robotic arm from the AI system. Neural network software can be integrated with any sorting technology, including optical sorters. So don't get a robot to get the AI, get a robot because it is the right sorting method for the station. Robotic sorters already benefit greatly from screening technology. Most robotic sorters are at the very back end of the system, with most of the screening and sorting already done. The lack of flexibility from being a human and the lack of a high pick rate make robotic sorters the lightest duty sorter available. One main benefit of robotic sorters is that they are easy to integrate and easy to remove, which makes leasing options viable. They can also fit in places other automation can't. So this video illustrates bad feed rate for a robot. Not only is there too much material, it's coming through in clumps. If material comes through in a clump, 1 item will be hit and the rest will be missed. This particular robot is supposed to pull aluminum cans out of the PET stream. But as you can see from this screenshot, it's missing quite a bit when they get too close together. Robots have the same issue as people when it comes to sorting high quantities of light items. A typical large MRF will have 2,000 to 4,000 pieces of film and flex packaging to pick every single minute. Picking this many items will require up to 70 robots doing nothing but picking film. So if you need to pick a lot of stuff, the go-to are optical sorters. Optical sorters are currently the workhorse of sorting in a MRF. They have a high throughput for sorters and a high flexible pick rate, anywhere from 100 to 2,000 picks per minute, depending on what you are feeding it, what task it is given. It can process up to 9 tons per hour of material. A high-speed paper optical sorter processes roughly 10,000 square feet of conveyor belt every minute, or 600,000 square feet an hour. That's more than 13 acres. You generally want 20% to 25% of the belt covered with material at any given time. If you put too much material, you start having overlapping items in collateral, reducing purity. And if you put too little material, you're producing less than you potentially could and losing yield. So what you have now is a wide, fast conveyor belt that you need to feed consistently within a narrow range of parameters. This is what makes optical sorters very sensitive to proper feed. Sorting efficiency drops very quickly once you pass 30% belt coverage, and not just 30% coverage overall, 30% coverage anywhere. These next couple slides will show you good and bad examples of optical sorter loading. Here we see 2 examples of belt coverage based on item count across the belt. On the top, we see an example of bad coverage, with a spike on the left side of the optical sorter and a slope down to the right. Any gray area is yield loss, so we want to minimize the gray area without exceeding the top line. On the bottom, we see an example of good coverage without spikes, which maximizes throughput and sorting efficiency. This type of good belt coverage can typically be seen coming off of mechanical screens, which is one of the benefits of actually still screening to help sorting. Now we see a time series of feed quantity. On the top, we again see an example of bad feed to an optical sorter, with peaks and valleys as material surges and then recedes. This is often caused by a cleated belt, which causes the same issues as feeding with a spike. You either lose capacity or lose the efficiency, depending on which poison you pick. On the bottom is an example of consistent feed over time coming from a screen or vibratory feed. Mechanical screens then maximize the utility of sorters. Now, one of the great things about optical sorters is that they have up to 250 individual effectors, each of which can fire many times a minute. In our experience, a high-speed optical sorter doing a quality control sort of paper will typically be able to sustain over 1,000 picks per minute. The best long-term pick rate we've seen is about 1,400 picks per minute. Presumably, if flex packaging is added, those rates could go higher. These are a lot of picks, and achieving this with manual sorters or robotic sorters is prohibitive, both in money and also just in having the space to do it all. Now that we've covered the basics of sorting, I want to take some time to explain how fractionating and concentrating material helps to not only increase sorter throughput, but also sorter efficiency. We're going to start by looking at a sample flowchart of a make-believe paper optical sorter working at 5 tons per hour input on a material stream that is 30% paper and 70% not paper. Now, that's a lot of numbers, so take a moment to digest. Now, even if we assume 95% efficiency, our end result is not great. Even though the optical sorter only misfires 5% of the time, it has a lot of chances to misfire on non-target material. So we end up with 89% pure paper at a yield of about 1.5 tons. This is a result of the stream not being concentrated to increase the amount of paper input to the sorter. If we compare this to a flow diagram that uses several stages of theoretical screening to concentrate the paper to a 63% input to the sorter, we see drastically better results. Now take a moment to look again. Running the same load through the same optical sorter with the same efficiency with a concentrated stream results in 97% purity and a yield of about 3.2 tons per hour. Because we've removed many of the non-desired items before sorting, we have fewer chances to misfire and more yield to dilute the misfire. This is another reason why you don't want sorters working on items that they aren't targeting. Not only are you wasting money making unnecessary decisions, evidenced by the reduced yield without screening, each and every sorter is going to make some amount of bad decisions. So you want to maximize efficiency by minimizing the opportunities for bad decisions. This is another benefit to a decision minimization strategy. Side by side, we see screening enhances throughput, purity, and yield of sorting. And check out that purity comparison. And keep that in mind. In the case of paper sorting, not only is paper concentrated, but the pass fraction of the sorter will remain concentrated and fractionated by physical properties. A MRF which processes flex packaging as well would then have a flex packaging fraction to be sorted after the paper is sorted. So you get a 2-for-1 impact of fractionating. The real MRF, you're probably also going to have small QC stations for both the sorted outputs, as well as a reclaim function for passed items. This is now looking more like what a real MRF process flow diagram would look like. And if we kept examining each fraction, we would eventually get there. But this demonstrates the point of screening enough, so let's just skip all that. Recall that the purity of the fractionated material is greater than the purity of the non-fractionated material. In our original serial flow diagram, we need to add QC stations as well. But instead of needing to remove 2% contamination, these QC stations need to remove 10% contamination, a much more difficult and expensive task. Now we need to give all 32 sort stations their own QC stations, and we end up with this mess, which is not ideal. A lot of us already knew all this on some intuitive level. This is why MRFs look the way they do. But what we're trying to do here is explicitly state the benefits of screening so that we can apply it to new situations. I'm speaking specifically about the sort station that receives no benefit of fractionation, no benefit of concentration, and no benefit of automation. I'm speaking about the pre-sort. Because of the challenges of the pre-sort, only manual sorting is available. And frankly, if someone develops a robot that can work on the pre-sort, they're probably going to wind up working for Google or DARPA or someone like that, or maybe causing the robot apocalypse. But because the pre-sort receives no fractionation, it is highly inefficient, highly expensive, and highly dangerous. You end up with 6 to 10 sorters swimming in this mess of material, trying to find the bad items. A sorter is maybe achieving 10 picks per minute here. The target material, large maintenance hazards, simply aren't concentrated enough to have enough targets. But then you end up with extra sorters in case people miss what they're supposed to sort under the pile of material. Pre-sorts are often the bottleneck to a system, so they're run fast at 300 to 400 feet per minute. And so the sorters are now trying to wrangle these large, dangerous items, which are moving quickly, while avoiding health hazards in the small fraction, such as needles and glass shards. And this is where the dreaded pause pedal comes into play. As a consequence, a sort station that exists to prevent downtime is often a major source of downtime in and of itself, so that sorters can work safely. So, how can we use screens to make this better? Let's take a look at a couple pictures of the pre-sort. This should be familiar. 6 to 10 people at this point in time trying to sort out of that. Many of them are not actively sorting, as you can see. Yet they need to be there to prevent wrapping and downtime. The pre-sort only exists in this case to protect the machines that come after it and prevent downtime, cleaning, and maintenance. But this gets industrial automation exactly backwards. Machines are supposed to help people work, not the other way around. So let's take a look at how this sort station looks with the help of machines. For comparison, here's a video of a large item post-sort which replaced the pre-sort. This is a system running the same tonnage in a demographically similar area to the two pictures on the previous slide. It is a much more efficient sort and a much safer sort as well, with 3 people doing the work of 6 to 10 because the target material is both exposed and concentrated. You can see the sorters working effectively on a fraction of the material. Now, because 60% of the material is removed prior to the sort station, sorters still have better visibility and accessibility to their target items. The small fraction material is bypassed as the large items a pre-sort is targeting are not present. So there's all the bypass material. Pre-sorters don't need to see that. Now, any sort station or sorting technology benefits from screening by fractionating, concentrating, and reducing the material as discussed. We've primarily discussed sortation of household and commercial waste thus far, but this holds true for C&D processing as well as anything else we need to sort. The benefit of screening is seen dramatically in comparing the old style pre-sort with the newer post-sort. Our goal in discussing the future of screening is primarily to continue to push towards screens that do not require a pre-sort. Some of you see the tension here, as pre-sorts in waste sorting primarily exist to protect the screens. And so we end up with a bit of a catch-22. We need sorting to enhance screening, but we also need screening to enhance sorting. Now, the way out of this is through better screening technology, so that screens can help people and can work as intended. Such screens before the pre-sort will also make MRFs robust to more material changes in the future. No matter how light the material gets, we're going to help the sorters on the pre-sort. So we don't have to end up adding more people or doing all the other things people are doing right now to get the pre-sort to work. Let's talk about existing types of screens. First and oldest way to screen is by size. Traditionally, this is done by trommel, vibratory screen, or disc screen. The second way to screen is by shape, also known as 2D, 3D separation. This can be done with disc screens and ballistic separators. Now, most of these types of screens are old as dirt, being used for centuries in industries like mining, aggregates, forestry, and agriculture. These are well understood, well documented machines. They were imported to the solid waste processing industry decades ago and are well studied here too. The paper you see in front of you is from the 1982 National Waste Processing Conference on the use of the trommel for screening solid waste. And we could spend hours and hours going over it and similar papers, looking at equations and diagrams and such. But this is absolutely no use to us here, as we're doing conceptual work. So let's just not. Instead, let's focus on some simplified parameters with which to compare machines. We're going to discuss throughput in terms of volume flow. This speaks to one of the main disconnects in our industry. All the financials are done in weight and tonnage, but all the machines processed by volume. So there's a constant discussion going on in terms of material density. And what we've seen in the last decade is that inbound densities have dropped and are continuing to drop. So MRFs have to process more and more volume of material in order to hit the same weight. So throughput of machines becomes more and more important as densities drop. Throughput is calculated by taking the 2D area of the material above the screen and multiplying by material speed. I've expressed things in terms of cubic feet per minute to minimize conversions and numbers and all that. But if you want cubic yards per hour, you can get a rough estimate of this by multiplying the numbers I'm using by 2. We're also going to discuss screening efficiency in terms of dwell time, agitation, and surface type. These machines work on probability rather than selectivity. So the longer an item stays in a screen, the higher the likelihood it will go the right way. There is a tension between throughput and dwell time because, obviously, the faster that material travels, the less time it will dwell in the machine. Agitation is important to get all items to the screening surface and becomes more important as OCC quantity goes up and densities go down. Anyone who has ever shaken a cereal box to try to get to the good bits should have an idea about how agitation works on bulk materials. Lastly, static screens build up paper mache or MRF mucus, or whatever you want to call it, over time, which causes holes to shrink, while active screens tend to not build up with material like that. Instead, those wrap. Here's some pictures of screens in case you didn't know what we were talking about. Trommels and vibe screens that are pictured use gravity to move the material, while disc screens use rotating shafts to convey the material. So, if we compare the throughput of the machines, the first thing that should jump out to you is the disc screen. This is why disc screens are everywhere in North America. Small, inexpensive disc screens can give the same throughput as much larger trommels and vibe screens. If we compare the efficiencies, some more advantages of disc screens appear. Trommels and vibe screens both run downhill, and there are physical and mechanical constraints to how big the machines can be. So dwell time is constrained, and increasing throughput always decreases dwell time in the tension I mentioned earlier. Disc screens, however, can be easily made longer by adding more shafts or decks, so you can hit the dwell and throughput parameters you need. Trommels have great agitation and can also open bags if needed, while vibe screens have by far the lowest agitation in the industry. This means vibe screens typically need more dwell time to hit the same screening numbers. Both have passive screen types that can gunk up, while trommels can wrap and vibe screens can spear. Disc screens avoid many of these issues, and so if they have such great performance, why are we even talking about replacing them? Well, you know why. Wrapping. This is the primary reason presorts exist in the current MRF. But recall, you need an army of robots to pull all the lightweight film in a system. So what are 6 to 10 people going to do with all this stuff? It just really doesn't make sense at a fundamental level. 2D, 3D separation is similar to screening by size, but the machines are also steeply inclined, so we have an additional factor of resistance from gravity. This allows flexible items to be separated from rigid items. Because of this resistance, shaped screens have all the same cost and more as size screens, but typically lower throughput, making them more expensive per ton or unit volume. Options are ballistic separators and disc screens. Now, as paper volumes fall in the MRF mix, as we've seen over the last couple of years, 2D, 3D separation is becoming less important, and in some cases is being skipped entirely to go straight to optical sorters. If flex packaging is added into the stream, 2D, 3D separation will regain its importance in order to process both flex and paper simultaneously as 2D volumes increase. Throughput calculations are similar to last time, with disc screens having a higher throughput due to a higher velocity. These screens are typically adjustable by angle and speed, and part of the reason for that is to not overload the paper sort station, whether manual or optical. A high-speed paper optical sorter usually wants about 100 cubic feet per minute of material. So the disc screen is throttled back, while the ballistic separator usually can't hit that target. Now, you can still use a ballistic to feed an optical sorter, and the optical sorter will work great on the lower amount of material, but you're not going to get the yield you want from one ballistic. These machines are more similar in screen efficiency unless the ballistic is overloaded, in which case rigid objects can't bounce and are carried up the screen. I'm sure some of you are thinking, hey, you're just bad-mouthing ballistic separators because you don't make them. But let's walk through a little thought exercise. Ballistics use the crankshaft to turn the rotating motion coming out of a gearbox into linear reciprocating motion, like walking. Each rotation of the crankshaft moves flexible material up the ratchet shape on the paddle by about the amount of the displacement of the crankshaft. This is typically 4 inches. Paper moves up the paddle 4 inches at a time because the paddle can't throw it. If you've ever tried to throw paper, not shaped like a paper airplane, picture what happens when you throw paper. So a 4-inch displacement times 120 RPM is 480 inches per minute, or about 40 feet per minute. In contrast, disc screens use shafts and discs, which are basically like wheels. The rotational speed of the perimeter of the disc is the circumference times the RPM. Just think of how the axle of a wheel rotates much slower than the perimeter of a wheel at the same RPM. So because we're using circumference, we gain an extra factor of pi. And who doesn't like pi? In addition, disc screen diameter tends to be between 9 and 12 inches. So we have that extra factor of pi and a diameter that is 2 to 3 times greater. Disc screens also tend to hover around 200 RPM nominal. So all these things working together, the wheel moves faster than walking. However, discs now have to be made of rubber to make sure all that rotational speed of the disc is imparted and translated to the material. Now, there's still a large degree of rollback and slipping, but the machine has velocity to spare. So if rotating, driven shafts give all these benefits of high throughput, good agitation, active surfaces, what is the drawback? Again, we all know the answer: wrapping. This is the reason we pre-sort and pre-sort some more and pre-sort some more. And our goal here today is to get rid of the pre-sort. So something has to be done. Now, we understand why people like ballistic separators, but in practice, they have less throughput than a high-speed optical sorter, which also has the benefit of not being confounded by the evolving ton, with flex packaging and film going in the 2D fraction on one end and 3D paper going into the 3D fraction on the other end. But optical sorters, which can replace ballistics, still benefit from better screening, as discussed. So we have, again, a conundrum: using screening to help sorting or using sorting to help screening. The way out is, as I've mentioned before, better screens. Now, do we try to improve the throughput of these machines that lack it? And some of these are old machines with limited room for improvement. Or do we try to retain the benefits of a rotating shaft, the whole reason disc screens have dominated the North American market, while solving the wrapping issue to the point where we can eliminate the pre-sort? So let's take a look at some of our design parameters. No pre-sort. And I'm not even talking, well, it can work without a pre-sort. I'm talking about no benefit to a pre-sort whatsoever. In our experience, if you hem and haw about whether something needs a pre-sort, you're going to end up with a pre-sort. In this case, maybe pretty much always means yes. Low maintenance, even and especially without a pre-sort. This includes the small fraction material, which won't have any pre-sorting at all. So even screens dealing with 5-inch minus need to be robust. Can handle any size material. Without a pre-sort, any and everything will be thrown into this machine. So it better be able to handle both the mattress test and the bathtub test, and the engine block test and the bollard test, and so on. Now, obviously, this constraint goes away somewhat when we're dealing with secondary screens handling small material. Unless someone conjures a mattress on the 5-inch minus line, you don't have to worry about it when you're dealing with smaller material, right? It must have high agitation, so we're not dealing with the throughput versus efficiency constraints. And it must also have high throughput to deal with the ever-lightening material stream. We're going to take a look at the trommel, the vibe screen, and the ballistic separator as 3 candidates which are sometimes run without a pre-sort. Now, recent developments in disc screens show a high circumference shaft significantly reduces wrapping, as items can't make it all the way around the shaft to start a wrap. So we're going to explore that as well. So we'll get to a comparison chart. There's our candidates. Here's our first condition: no pre-sort. People have tried disc screens without a pre-sort. It's a bad idea, no matter the circumference. I've seen systems running with vibe screens or ballistics as the OCC screen without a pre-sort. These are, however, small systems with low throughput. And we still want high throughput systems, no matter the automation level, because all other things being equal, more is better. Low maintenance, pretty much the same two candidates. Maybe you can add trommels to this category if they're to your taste and they're designed right, but a lot of people would still disagree with you. Able to deal with large items. Vibe screens can do it with gravity, and disc screens can do it with driven shafts. Trommels are a constrained space that can choke up on large items or drop heavy items too far. And then a mattress on a ballistic just kind of hangs out there. This constraint goes away for secondary screens, as discussed. Now, high agitation pretty much crosses vibe screens off the list, while the rest do a good enough job. High throughput. A trommel can be made big enough and with enough agitation to get it done. Maybe a vibe screen in the right application, but this is where the lack of agitation really hurts. And certainly a disc screen has the throughput we need. These constraints we're looking at are highest for primary screens and decrease the further into a system you get as machines get smaller and lighter duty. And some people are okay with cleaning wrapping off a high circumference disc screen for 15 minutes or so every shift. And some people are okay with the low throughput of a ballistic if it's at the back where throughput is less important. These are still good machines, but neither of these would go in the front to help out the PRESORT. Now, from our internal discussions, the vibratory screen is still the most likely candidate so far for primary screening, but it has its drawbacks in its sorting efficiency due to the limited agitation. Now, that said, we see that nothing checks off every box or even really gets close. We're not going to add high agitation to a vibe screen, and trommels and ballistics are pretty much going to struggle with large items in a way that makes you want to add a PRESORT. Now, our last option is to keep the rotating shafts of the disc screen, but solve the wrapping issue. And I'm not talking about solving the wrapping issue the way people have said they did with disc screens for the last 20 years or so, but then not really. We need to keep the rotating shaft, but change something about that shaft to prevent wrapping. Now, what we end up with is an auger screen. We retain all the benefits of a rotating shaft, but each shaft is also a screw conveyor, continuously stripping wrapping material off of adjacent shafts. This checks 4 of the 5 boxes, but we still lack the agitation because screw conveyors and augers are around. We have, at this point, run auger screens without a PRESORT or a pre-shredder in residential and commercial waste for roughly 3,000 hours, either in prototyping or commercial operations. In that time, the machines have been cleaned by humans of a total of 1 wrapped item. These rotating screws can handle any sized items at high throughput and keep running all day without performance degradation. Now, if you check this video, you can see the high throughput. You can also see the lack of material agitation, and you can see the 3 sorters working in the background. So this is the same system from earlier, but from the opposite direction, where we see the auger screen working to reduce the material to the PRESORT. Our recent developments have added high agitation to augers as well, so we can get better screening efficiency and really check all the boxes of what screening in the future will look like. And these screens can work in basically any application or material. We still have a long way to go developing this and finding all the right fits within a MRF. But the moral of this particular story is that the PRESORT, or what used to be called the PRESORT, is finally getting some love and attention. So what will be the MRF of the future? There are still a lot of unanswered questions. How do we efficiently sort all these small boxes that seem to spread everywhere? Where do we put the chipboard, which is up to 10% of the material stream that nobody wants to put anywhere? We don't want it in the OCC. We don't want it in the mixed paper. We don't want it in the residue. Where does it go? What are we going to do when flex packaging increases volumes of low-weight materials? In order to deal with these more difficult sort tasks, we need to maximize our sort efficiency by maximizing our screening efficiency and minimizing the cost of doing so, and apply this to all sort tasks, including the PRESORT. Eliminating the PRESORT is a big, necessary step along the way to this MRF of the future. Now that about wraps it up. I would like to thank you all for attending this webinar. For more information on our products and services, you can visit our website at cpgrp.com. Please also connect with us on social media. Thank you.